Hello everyone. In this video, we are going to talk about a specific process injection technique, which is process hollowing. So earlier I thought that I will be doing a static analysis of a malware which is dependent on doing injection by making use of process hollowing. But when I was making the video, I came to conclusion that if I go through the step-by-step process of how process hollowing works and do a behavior analysis instead, then you will be able to understand it more clearly, and then you can go on to analyze the malware which depends on process hollowing. So here I have a MITRE attack framework of process hollowing open, and the attack ID for process hollowing is T1093, and process hollowing occurs when a process is created in a suspended state when its memory is unmapped and replaced with malicious code. The MITRE attack framework gives you an overview and also gives you references to the examples and the malwares which use the process hollowing techniques. So in the procedure examples, we can see that we have a list of various malwares that depend on process hollowing, and in this the most famous ones are URL sniff and smoke loader. If you want to get more information about a specific malware, you can click on the references. So let's click on the Duku malware, which is capable of loading executable code via process hollowing, and we can see that it opens up a semantic analysis page which has a complete analysis of this type of malware. This framework also tells you how you can mitigate such type of attacks and how you can perform the detection of process hollowing. So the process hollowing technique was created by a guy named John Leach from AutoSec Tools, and he has created a great explanation which you can find in the PDF folder. It also contains the source code in the executable file. So in this example, it contains an executable name helloworld.exe and processhollowing.exe. So the processhollowing.exe will inject helloworld.exe into a legitimate executable, which in this case will be svchost.exe. So when we execute helloworld.exe, a message box pops up. So the helloworld.exe is a simple message box executable, and let's now see how the process looks like when we execute processhollowing.exe. So let's open up Process Explorer and execute process hollowing. So we can see that the message box pops up and a new process gets created, which in this case is svchost.exe. When we see the properties of svchost.exe, we can see that the parent process of this process is process hollowing and the command line is svchost. We can also cross-check this if this is the process from where the helloworld.exe is executed. We can go on strings and click on memory, and we can click on find to find our string, which is hello world. So we write hello and click on find. So we land at the hello world string, and we can see that this is the exact process which was hollowed out with the messagebox.exe executable. Now let's have a look at the source code of the processhollowing.exe, and let's single step through the code in the Visual Studio. So let's break at the create hollowed process, in which we are passing the first arguments as the process is the target process and the path of the executable that we want to load. When we land at the create hollowed process, the destination command line is svchost and the source file is messagebox.exe. We initialize some structures which will be used when we call create process A, and when we call create process, we are passing destination command line with the flag create suspended. So when we execute this, we will see in the process explorer that a new process svchost.exe gets created in the suspended state. Now we are trying to read the process environment block from the created remote process, and from the process hacker we can see that the PEB is located at 26B6000. The reason we are trying to read the process environment block is because it contains the address at which the svchost.exe executable code is loaded at. So we will step through the process and we will see, and at the end we will get the address from where the svchost.exe executable was loaded, so we can pass it to the unmapping function, which in this case would be anti-unmap view of section, so that we can remove the legitimate executable and write our malicious, which in this case is messagebox.exe. The function read remote peb calls find remote peb, which at the end calls anti-query information process, which fills up the process basic information structure. And the structure contains the PEB base address. At the PEB address, when we go to offset 16, which is hex 10, we can find that the address, which is in Latin Indian, which will be read as 00540000, which is the address of image svchost.exe. So when we call read process memory, this information will be filled in the PEB structure, and at the end we return this PEB structure. We can also cross-check this base address of svchost.exe when the read process memory gets called and the PEB structure gets filled. So when we step through this function and open the PEB structure, we see in the image base address, the address is 540000, which is exactly same that we saw in the process hacker. So now this information is read, we return the PEB structure. After that we call read remote image, which gets the information of the legitimate executable, and the information that it collects is DOS header, file header, number of section, and the section information. We now open the message box executable by calling create file A and passing it the flag generic read and open always. We then get the size of the file by calling the API get file size, and read the file by calling read file. The function get loaded image gets the information of the message box executable, and the information that it collects is the file header, number of sections, and the section information. It then gets the header information by calling get anti headers, and then gets the address of anti-unmap view of section by calling get proc address. This function, anti-unmap view of section, is the routine which unmaps a view of section from the virtual address space of the subject process. The first argument is the handle of the process, and the base address is pointed to the base virtual address of the view to unmap. So before calling this function, if we look in the process hacker, the memory regions, so the address that we are unmapping is 540000. So right now we can see this address, but when we step through this function and refresh the memory region, we see that the address has disappeared. Now to write the message box executable into this remote process, we have to call virtual alloc ex, through which we are able to allocate memory into the remote process. We pass it the flag of the address where the allocation has to be made by passing it the parameter PEB image base address, which if we remember was 540000, and the size that is being passed is the size of image of the message box executable. We make the memory region as page execute read write. Now when we have a look at the Process Explorer memory regions, we see that a new memory region with the same base address has been allocated with the protection as read write execute. Now we calculate the delta between the original image base address and the image base of the message box executable. The image base of message box executable in this case is 4 followed by 5 zeros. This delta is calculated so that if the executable contains a relocation section, the image has to be relocated by this amount of delta. We assign the image base address to the executable's image base, and by calling write process memory, we are writing the headers into the image base address. So we can see in the memory that when we click on this memory region, you can see that the header information, the magic MZ and magic PE has been written into this memory region. Now the message box executable contained 5 sections. So by looping through all these sections, we are writing all these sections into the remote process by calling write process memory. And since the delta was non-zero, the base relocation have to be applied to this memory image. Now we calculate the entry point by adding the image base address to the address of entry point of message box. So the address of entry point in this case is 11CF. We can also see that if all the information has been written to the this memory, and by scrolling we can see that all the section information, all the header information, everything has been written. We now have to get the context of the process, and we do it by calling getThreadContext, in which the first argument is a handle to the thread whose context is to be retrieved, and the second argument, context, is a pointer to a context structure that receives the appropriate context of the specified thread. When we step through this function, we can see in the context structure that information like DR0, DR1, some segment register GSFS, and the register like EDI, ESI, EBX, EAX information is located within this structure. We now set the EAX register to the DW entry point that we calculated earlier, and by calling setThreadContext, we set the context of the svc host.exe thread. We do this so that as soon as we call resume thread, the address that we have set in the EAX register now starts to execute at the entry point of the message box executable. So earlier the EAX register was pointing to the entry point of the svc host.exe process. So when we set the EAX register to the entry point of the message box executable and we call resume thread, the message box executable will now execute. Before calling resume thread, we can see in the Process Explorer that it is now in the suspended state, but when we call resume thread, the svc host.exe starts executing, and we can see that our window has popped up. From the detection point of view, we can see that if a person is looking at the Process Explorer without going into the properties of each running process, he would not be able to identify which is the malicious process. But if we open up the svc host.exe properties, we can see that the parent process is still process_hollowing.exe. So as a defender, I will be quite sure that some type of process injection has taken place, because the parent process of svchost.exe is always services.exe, which is run by the anti-authority system, and svchost.exe hosts some kind of services which we can get the information from the command line. But in this case, the command line is svchost, so it is not executing any service. So that can be another parameter that this process is hosting some kind of malware. Now the services executable, which is services and control application, is ran as a system application. Now to add more stealth, what we can do here is we can change the parent process to services.exe, but since that process is running as a system process, we have to have system privileges to open and handle to that process. That could be completely done, but for this example, let's choose a different process. So we have taken in this example the Explorer process, which will be parent process of svchost.exe. So let's go into Visual Studio and change the parent spoof to true. So what we are doing here is we are first getting the handle to the Explorer process. So we get it by calling the function getExplorerPID, which would call createTool help32 snapshot, which will create the snapshot of all the running processes at that instant of time. Then by calling process32 first, it will walk through all the processes list and check to see if the process name matches with the target process, which in this case is explorer.exe. When we get the process ID, we call open process with process all access and return the handle to the process in hExplorer. We then call initialize proc thread attribute 2 times. The first time that we call is because to get the size of the attribute list length, so that much amount of memory can be allocated by calling heap_alloc. So what this function does is it initializes the specified list of attributes for process and thread creation. So the attribute that we want to add is added by calling the API update proc thread attribute and passing it the argument proc thread attribute parent process, which is a pointer to a handle to a process to use instead of calling process as the parent process for the process being created, which in this case is the Explorer process whose handle is being passed in the next argument. And in the create process function, we have to pass extended information present and pass it the extended structure, which contains information like if the window is to be created or not, the specific x and y coordinates to show where the window has to be created, and so on. We can also change the title of the console process. Now that we have gone through this function, let's compile this solution and let's directly execute process_hollowing.exe. Let's open Process Explorer and click on Properties of svchost.exe. We can now see that the parent now contains explorer.exe and the PID is 12464, which is exactly same as the Explorer process. To add more stealth, you can also change the command line, and it is quite easy to do that also. Now let's come to detection. To detect process hollowing, whether any process has been hollowed out within the current system or not, the repository created by Hashezadeh called Hollows Hunter scan through all the running processes within the system and finds out the replaced or implanted portable executable shell codes hooked function or the in-memory patches. So let's go to tools and execute Hollows Hunter. So when we execute this, we will see many warning and errors called access denied. Try to run the scanner as administrator. This is shown because many processes are running as system process, and this command.exe is a medium process, so it cannot get the handle to that process. But since the svchost.exe process was running as a medium integrity process, it should be able to find out. So at the end, we can see that it has shown that the summary includes the name as svchost.exe and the PID 9508. It creates a folder and summary.json. When we open summary.json, it includes a suspicious attribute which contains PID name, replaced and implanted. So the process was replaced and implanted, and inside the folder process 9508 contains an executable which was dumped out from that memory region. So opening this in CFF Explorer, we can see that it is a valid executable file, and we can cross-check this. If this was a message box executable, we can open this inside of Ghidra, and when we go to the main function, we can see that our call to message box function is there. So the tool Hollows Hunter is dependent on the library named PECEIV, which is also written by Hashazadeh. By using that executable, we can give it the target process from which we have to find out whether the process hollowing was done or not. So let's also try that tool. So we pass the parameter PID of 9508, and we can see that it is scanning all the modules, the executable and DLL files, and at the end it shows the information that report dumped to process 9508. So the way it works is, it goes through each memory region and checks to see where the executable or DLL file is located. If it finds an executable or DLL file within a memory region, it checks to see if that executable is located on the disk. If it was not located on the disk, it can be quite sure that it was manually mapped within the process. If you want to detect other process injection techniques, there is a PowerShell script named as getInjectedThread. It detects classic DLL injection, reflective DLL injection, and memory module based injection. So that's all for this video. In the next video, we will be going to look at credential stealing malware, and we will be having a look at the Windows Vault, which is a credential manager available inside of Windows. So that's all for today. Thank you and have a nice day.